Consider the following region R and the vector field F. So here we're given the vector field in terms of x and y, defined by components 2y and 2x. And our bounded region R is the triangle with vertices at the origin, at the x-intercept 2, 0, and the y-intercept 0, 1. And we're asked to compute the two-dimensional divergence, then evaluate both integrals in Green's theorem, the flux form, and then to state whether this vector field is source-free. So we want to start here by recalling the flux form of Green's theorem. So with the flux form of Green's theorem, we are taking the line integral over the closed curve C of our vector field F dotted with the normal vector integrated with respect to the arc length. You can use an equivalent form here. Again, the line integral over the closed curve C of f dy minus g dx. So this is the flux line integral. And Green's theorem shows us that we can convert this line integral to the double integral over R of the two-dimensional divergence, the partial derivative of f with respect to x, plus the partial derivative of g with respect to y dA. So this is the line integral and equivalent double integral of flux forms of Green's theorem. So to get us started here, let's compute our two-dimensional divergence. So we are looking for the divergence of our vector field f, which again is the integrand of the double integral. So that's the partial derivative of f with respect to x plus the partial derivative of g with respect to y. And here we are given the vector field f of x, y. We can think of these components, this is f and g. And so here, f is 2y, and g is 2x. So we can see that the partial derivative of f with respect to x is going to be 0, and the partial derivative of g with respect to y is also going to be 0. So therefore, the divergence of this vector field is equal to 0 plus 0, which is simply 0. So we want to recall that when your divergence of a vector field is equal to 0, this means that the vector field is source-free. So we have answered parts A and B, parts A and C in one sweep. So now we want to go ahead and evaluate this using both integrals of Green's theorem. So for part B, we'll have two parts here, the line integral and then the double integral. So we'll start by evaluating the vector line integral. That's going to be the integral of the closed curve C of f dy minus g dx. So in order to see what our closed curve is, we need to go ahead and sketch this region. So we want to sketch the triangle with vertices at the origin. So at 0, 0, we have the x-intercept 2, 0, and then the y-intercept 0, 1. So in our Cartesian coordinate system, we have the y-axis and the x-axis. So labeling our given ordered pairs here. Again, we have a vertice at the origin, a vertice at the ordered pair 2, 0, and then a third vertice here at 0, 1. So our bounded region is the right triangle. So we want to be mindful here, if we're evaluating a vector line integral, we need to be mindful of each curve's orientation. So we'll say that this, on the x-axis, is our first curve, moving from the origin to the ordered pair 2, 0. we have three curves here. Our first curve is y is equal to 0 at the curve representing our x-axis from the ordered pair at the origin 0, 0 to the ordered pair 2, 0. So in other words, we can think about this as x equals 0 to x equals 2. And writing this as a vector-valued function, our parametric description, x of t, y of t. So here we have a smooth curve, y is 0, so we let x be t, and y is 0. And this is for t greater than or equal to 0, less than or equal to 2. And again, this is our first curve here. We have 2 more to go. So now going back to our sketch here, we are starting at the ordered pair 2, 0 and moving in a counterclockwise direction from the point 2, 0 to the point 0, 1. And this line, this is our second curve c sub 2, just represented, but if we use our point slope form or slope intercept form, we can find the equation of the line here is going to be minus 1/2 x plus 1. So in defining this, our second curve, c sub 2, we have y is equal to minus 1/2 x plus 1 from the ordered pair 2, 0 to the ordered pair 0, 1. So in other words, we're moving from where x is equal to 2 to the x value, x is 0. So our bounds are changing here. And if we go ahead and write this as a vector-valued function, r of t for our parametric description of this line segment, we have x of t, y of t. So x, again, here we have a smooth curve, so we're simply replacing x with t, and then y is defined as negative 1/2 t plus 1. And now again, keep in mind this is x, or this curve is moving from x equals 2 to x equals 0. So we would say that t here is greater than or equal to 2, less than or equal to 0. And again, going back to our sketch here, we are now at this ordered pair, 0, 1, and we're moving in a counterclockwise direction from the ordered pair 0, 1 to the origin 0, 0. And we can think about this third curve here, c sub 3, as the vertical line x is equal to 0. So we can say that c sub 3 is defined by the curve x equals 0 from the ordered pair 0, 1 back to the origin 0, 0. So here, because our function is defined in terms of x, this is moving from where y is equal to 1 to where y is equal to 0. We need to give ourselves a little bit more room. So therefore, the parametric description of this line segment, vector r of t, again with components x of t, y of t. So here we have the smooth curve, x is equal to 0, so x of t is 0, and we're letting y be t. And again, looking at the bounds on y of our smooth curve, we can say that this is for t greater than or equal to 1, less than or equal to 0. So with these three curves here, we can see that we're going to need to have the sum, or when we evaluate our vector line integral, we're going to have the sum of 3 separate pieces. So our vector line integral of the closed curve C of the vector field dotted with the normal vector ds will need to be evaluated as the vector line integral of C sub 1 plus the vector line integral of the second curve C sub 2 plus the vector line integral over the curve C sub 3. All right, so here we go. So let's think about our first curve here, C sub 1 Again, that's vector r of t with components x of t, y of t, which we have defined as t, 0, for t greater than or equal to 0, less than or equal to 2. So let's set up our vector line integral here and then evaluate. So the first thing that we need to do is take this vector field defined by the components 2y, 2x, and parameterize it. So we want to substitute this vector value function in and simplify. So we are going to replace the y and x of the original vector field with the y and x of the parameterization. So this becomes 2 multiplied by 0. And then we have 2 multiplied by x, which is t. And so we can simplify this parameterization of our vector field as the vector 0 to t. And we want to keep in mind that these components can be represented as f and g for our line integral evaluation. So we also need to go ahead and find the differentials here. So using the components of our parameterization, we know that x of t is defined as t. So if we differentiate this with respect to t, we have dx dt is equal to 1. And then multiplying both sides of our equation here by dt, we can solve to find the differential dx is equal to dt. And then we want to do the same thing for y of t. So here y of t is equal to 0. So the derivative of y with respect to t is simply 0. And again, if we multiply both sides here by dt, we can see that dy is equal to 0. All right, so we have everything that we need now. We have the parameterized vector field as well as their corresponding differentials. So we can set up our line integral. So this is the line integral over the first curve c sub 1 of f dy minus g dx. So this is the curve, or the integral from 0 to 2. And plugging in what we just found, we have our f coordinate is 0, multiplied by dy, which is also 0, minus g, which we found to be 2t, multiplied by dx, which is dt. So this is the integral from 0 to 2 of negative 2t dt. And when we integrate, we have minus t squared from 0 to 2. And then when we evaluate, we have minus 2 squared gives us 4, minus 0, for a beautiful final answer of negative 4. So there's our first integral, and we're ready to do the same thing for our second and third curves. So c sub 2 is represented by the vector valued function, or the parameterization, vector r of t. And here we found x again to be t. Y is minus t by 2 plus 1. And here the t values are where t is greater than or equal to 2, less than or equal to 0. So we need to parameterize the vector field. So this is going to give us, we'll have components 2 multiplied by y of t, 2 multiplied by x of t, and plugging in the corresponding components here, we have 2 multiplied by minus t divided by 2 plus 1, and 2 times t. So this parameterization of our vector field simplifies to, again, these are the components fg. And if we simplify f, if we distribute this 2 through to both pieces, we are left with minus t plus 2, 2t. And we need to find our differentials now. So again, we're using the coordinates of the parametric description of c sub 2. So we have that x of t here is defined as t. So dx equals dt. We have the component y of t, which is defined here as minus t divided by 2 plus 1. So the derivative of y with respect to t is equal to minus 1/2 dt. And we're ready now to compute this vector line integral. So the vector line integral over c sub 2 of f dy minus g dx. So plugging in what we just found, we have the integral now from 2 to 0 of our f component, which is minus t plus 2 multiplied by dy, which is a minus 1/2 dt, minus our g component, which is 2t, multiplied by dx, which is dt. And so simplifying this, we have the integral from 2 to 0. Again, we're going to take this and distribute it through to both pieces, which leaves us with t over 2 minus 1 minus 2t. And I've factored that dt outside. And we'll need to get a common denominator here to combine these two t terms. And this becomes the integral from 2 to 0 of minus 3/2 t minus 1 dt. And when we integrate, we're left with minus 3/4 t squared minus t from 2 to 0. So when we plug 0 in, everything cancels to 0. And then we are subtracting minus 3/4 multiplied by 2 squared, which gives us 4, minus 2. So we're left with a minus 5 for a beautiful final answer of 5. So that is the value of our second curve here, and we have one more to go. Our third and final curve is going to be a vector-valued function, r of t. We have components x of t, y of t, which we've defined as 0t. And this is where t is greater than or equal to 1, less than or equal to 0. So we want to, again, use this parametric description to parameterize the vector field. So this is going to be 2 multiplied by y of t, 2 multiplied by x of t, and plugging these components in, we're left with 2t, and then 2 times 0 leaves us with 0. And then we'll keep in mind for our integration that these components are represented by f and g. And now we want to go ahead and find our differentials for dx and dy. So x of t is 0, letting us know that dx is 0. And then the y of t component is defined as t, so dy is equal to dt. And we're ready for our line integral. This is the line integral of the third curve, c sub 3. Again, of f dy minus g dx. So we have the integral from 1 to 0 of 2t multiplied by dt minus 0. So this line integral simplifies to the integral from 1 to 0 of 2t dt. And integrating, we have t squared from 1 to 0. So that would be 0 minus 1, leaving us with a beautiful final answer of -1. So now that we have all three components, we're ready for our final answer here. Again, this is the closed curve C of the vector field F dotted with the normal vector ds, which we split into the three pieces, c sub 1 plus the vector line integral over c sub 2 dotted with the normal vector plus the vector line integral over c sub 3. So we found that the vector line integral over the first curve was negative 4. The vector line integral over our second curve, c sub 2, is 5. And then last but not least, the vector line integral over the third curve was minus 1, which leaves us with a final answer of 0. So this is Green's theorem using our vector line integrals, which is certainly the longer way to compute this problem. So what we want to do now is quickly look at the double integral of Green's theorem. So our double integral here is the double integral over R of the two-dimensional divergence, the partial derivative of f with respect to x, partial derivative of g with respect to y, dA. And let's keep in mind the very first thing that we did was compute the two-dimensional divergence, and we found it to be 0. So this is the double integral over R of 0 dA, which equals 0. And this matches the vector line integral that we just found. And so we have confirmed that this vector field is source-free.